Hey guys, this looks like a fun one. We're given 5 equilateral triangles. This largest one has an area of 14, and I want to know what's the total area of the other 4 triangles. If you want to try it on your own, pause it right now, because I'm going to solve it in 3, 2, 1. Since we're dealing with equilateral triangles, we should use these notes right here. It gives us the height of the triangle in terms of the side lengths, and also gives us the area of the triangle in terms of the side lengths. Now that I'm thinking about it, do we really trust these notes? How are these notes made? Let's see if we can figure this out on our own. Let's start with an equilateral triangle, and let's call each of the sides S. Let's draw the altitude of the triangle, which will be at right angles, and let's label it H for height. This will also cut the base in half, so each of these 2 parts have a length of S over 2. Let's focus on this right triangle here, and let's do Pythagorean theorem. It'll be S over 2 squared plus H squared equals S squared. For this S over 2 squared, the square can go to both the top and the bottom, giving us S squared over 2 squared. And 2 squared is equal to 4. Next, we can subtract S squared over 4 from both sides. On the left-hand side, we'll have H squared. And on the right-hand side, S squared minus 1/4 S squared is 3/4 S squared. Next, to get the H all by itself, let's take the square root of both sides. Since H is a positive distance, the square root of H squared is H. And on the right-hand side, for everything under the square root, they can each get their own square root. On bottom, the square root of 4 is 2. And then since S is a positive distance, the square root of S squared is S. And now we know that the height of an equilateral triangle is exactly √3 over 2 times the side length. And then to find the area, it's 1/2 base times height, where the base is equal to S and the height is equal to H. And in the place of this H, let's plug in the √3 over 2S. Let's rearrange things a little bit. 1/2 times √3 over 2 is √3 over 4. And S times S is S squared. And now we have the area is equal to √3 over 4S squared. Let's change the base back to S and smush everything together. We can give it a label and put a box around it. And now we just derived the notes that we already had. That was productive. Now we can use these notes with confidence. Let's call the side length of this equilateral triangle X. Let's call the side lengths of these 3 triangles Y. Does that make sense? Y. And let's call the side lengths of this triangle Z. And I think it's safe to assume these 3 green equilateral triangles are congruent. And now using these notes, we can find the areas of these triangles in terms of Y and Z. The areas of the green triangles will all be √3 over 4 Y squared. And then for the yellow triangle, the area will be √3 over 4 Z squared. And the question we're trying to solve for, the total area of these 4 triangles, will be 3 of these green triangles plus 1 yellow triangle. And each of these terms contains a √3 over 4, so let's factor out √3 over 4. And this looks important, let's put a box around it. This is what we're trying to solve. Once we know this, we'll know the answer to the question. And now we're done with these. And then let's do the formula for this triangle. The area of this triangle, which is 14, would equal √3 over 4x squared. This also looks important. Let's put a box around it. And now I think we're done with these notes. And now from here, we need to find a right triangle somewhere that contains x, y, and z. Let's do this right triangle here. We already know the hypotenuse is x. Let's cut the base up into 3 portions. The first portion is the same length as the side of one of the green triangles, so it's equal to y. And the second portion is exactly half of one of the sides of the green triangles, so let's call it y over 2. And this last portion will be exactly half of the yellow triangle. It'll be z over 2. And then to get the height of this red triangle, it is the height of the yellow triangle minus the height of the green triangle. Let's call it h sub z minus h sub y. That's just a temporary notation for the height of the z triangle minus the height of the y triangle. And now we have everything we need to do the Pythagorean theorem. It'll be this side squared plus this side squared equals x squared. And before we do all this, let's make these h's what they're supposed to be. Let's bring back these notes. And the h is equal to √3 over 2 times s. So the height of a z triangle would be √3 over 2z, and the height of a y triangle would be √3 over 2y. And now we're ready to do the Pythagorean theorem. For the first side squared, after we multiply this out, we get this here. And then to multiply all this out would give us this here. And it's still equal to x squared. Now we do have some like terms. Let's move things around a little bit. 9/4 y squared plus 3/4 y squared is equal to 12/4 y squared. And 12 divided by 4 is equal to 3. And then for these two, 1/4 z squared plus 3/4 z squared is is equal to z squared. And then for the 3yz over 2 minus 3yz over 2, one's positive, one's negative, so they're going to cancel each other out. And now we have 3y squared plus z squared equals x squared. And 3y squared plus z squared is part of the formula we were trying to solve. Since this is equal to x squared, in the place of this, we can plug in x squared. And now we have the area is equal to root 3 over 4 x squared. And earlier we showed that root 3 over 4x squared is equal to 14. So in the place of this, we can plug in 14. Let's give it a label of square units and center it in the box. This is the answer to our question. In this diagram, the total area of these 4 equilateral triangles is equal to 14 square units. It ends up being the exact same area as this triangle. How exciting.